Hello folks, this is a extra special video made specifically for my 11-12 and 13-14 AP Calculus class on Thursday, March 16, 2017. Unfortunately, I have to go to a meeting this afternoon, and there's some very important example problems we didn't get to in class yesterday, so here's your chance to catch up on those. We did the front page of the notes yesterday. I want to remind you of a very important property of particular solutions to differential equations. They cannot cross an asymptotic differential equation, and we must restrict the domain of the particular solution to a single open interval that contains the initial condition. Okay, that's very important. You should have that written down from yesterday. So what are we going to do now? Well, we're going to go to page 2, and we're actually going to solve example 7 and then example 8. For example 7, we're given the differential equation xy prime plus y equals 0. And the first thing we're asked to do is find the general solution to this differential equation. Remember the steps from page 1. We're going to write, separate, integrate, and rewrite. So the first thing we have to do is get this thing into a form of dy dx equals something. So we're going to go ahead and rewrite it as x times dy dx plus y equals 0. So y prime is the same as dy dx. You've seen that for about 7 months now. That shouldn't be new. But what we have to do is a little bit of algebra to get dy dx all by itself. In order to solve for dy dx, we're going to have an equation that looks like this. Dy dx equals negative y over x. So our next step is to separate variables. So we're going to end up with 1 over y dy equals negative 1 over x dx. And it's worth noting that I chose to keep the negative sign on the right-hand side of the differential equation before we integrate. And your goal, anytime you're doing a solving a differential equation, should be to leave the simplest thing you can over on the left-hand side. So try and get rid of any constants, try and get rid of any negative signs, leave them on the right-hand side whenever possible, because it's going to simplify your solution in the end. Okay, next step, step 3, is to integrate. So we're going to take the integral of 1 over y dy, and then the opposite of the integral of 1 over x dx. And when we do that, we should get the natural log of the absolute value of y equals negative natural log absolute value of x plus an arbitrary constant. Okay, so now we're ready to go to step 4 of our differential equation solving procedure, which says write y equals f of x if possible. So this one's kind of challenging, and what I'm going to do is take you through some steps. The first thing I want to do is I want to get rid of this negative sign here. I can do that by using a property of logarithms called the power property. And now that I have x to the negative 1, that's really 1 over x. So let me go ahead and rewrite this whole equation. I have the natural log of the absolute value of y equals the natural log of the absolute value of 1 over x plus a constant, because x to the negative 1 is the same as 1 over x. Now, a lot of you want to just simply, at this point, maybe cry a little bit, because how on earth are you going to write this as y is a function of x? Well, we're going to exponentiate this. Remember that the natural log of the absolute value of y means that the output of that is the exponent that you would put on e to get the absolute value of y. So this can be rewritten as the absolute value of y equals e to the natural log of the absolute value of 1 over x plus a constant. Well, if you recall what we did yesterday, we talked about e raised to a variable expression plus a constant can be rewritten. So I'm going to rewrite this as e to the natural log of the absolute value 1 over x times e to the c. Now this whole thing here, e to the c, is a constant. I would like to keep it, I would like to just call it c. If I do that to be mathematically correct, I better go back and change all of these other constants and call them c sub 1, because I don't want to, I try to be careful with my constants and not use the same name for two different constants. All right, and if you recall, there's another property of natural logs and base e that says e raised to the ln of 1 over x is just equal to 1 over x. Actually, absolute value of 1 over x, because that's what I have there. So I'm going to rewrite what I have here. I have, on my left-hand side, I have the absolute value of y. And then on my right-hand side, I have c times the absolute value of 1 over x. And the absolute value of 1 over x is the same as 1 over the absolute value of x. So let's just write it like this. And that is our general solution to this differential equation. Before I go on to part B of this problem, I'd like to make a bold statement. I would like to say that we can actually rewrite this as y equals c over x. And then I want to ask you a question. Why is this okay? Is it okay to just use an eraser and erase absolute value symbols at will? Absolutely not. There's a reason why these two are equivalent, and we'll talk about that in just a second. Let's go back up here and look at part B of this question. Is the domain of the differential equation restricted? The answer to that question is yes. And we need to look back at our original differential equation to identify that domain restriction. The domain of this differential equation is x cannot equal 0, because then we'd have a division by 0 error. Okay, so let's state the domain is x cannot equal 0. That's very important. Is there anything in the solution we should consider? Well, absolutely. We should consider this thing down here about why did I just erase the absolute value symbols. That's normally not legal. Remember, if you ever just erase something in a problem, the eraser strategy doesn't work. Okay, you need to have more mathematical reason behind it than just I use my eraser. So here's what I'd like you to consider. Absolute value of y equals c over the absolute value of x is equivalent to y equals c over x because, drum roll please, c can be positive or negative. If we think back to the piecewise definitions of absolute value of y and absolute value of x, we're going to have an equation that looks like y equals c over x, but sometimes the y will have a negative sign in front of it, and sometimes the x will, and maybe they both do. But remember, c is a constant that can be any real number. That real number could be positive or negative. So the fact that c can be any real number, that takes care of all of our absolute value problems. And that's why it's justified in this instance to state that absolute value of y equals c over the absolute value of x is equivalent to y equals c over x. I do have a cautionary statement here. I want you to be careful with absolute values in your general solution and particular solution. Okay, so I want you to use caution if your general solution includes a sum or difference. If your general solution includes a sum or difference, you need to be very careful with the absolute value. In that case, more than likely, you will need to consider the piecewise definition of the absolute value functions. Let's move on to part C. The last part of this problem says, what is the particular solution through negative 2 comma 4? So this is pretty straightforward at this point. We're going to sub in negative 2 comma 4 to y equals c over x. That's going to give me 4 equals c over negative 2, which says that c equals negative 8. Let's go ahead and write our particular solution. It's going to look like this. Y equals negative 8 over x. And if you just put a box around this and say you're done, I'm going to tell you that you are wrong, because you have neglected the big idea from page 1, bottom of the page, that says particular solution cannot cross an asymptote. We must pick a single open interval that contains the initial condition. Well, in this case, my initial condition has x is less than 0, so I have to restrict the domain on this particular solution so that x is less than 0. Now we have a complete and correct solution. All right, I'm going to go ahead and do number 8 for you here. I'm going to fast forward it. I would like you to pause the video, try it on your own, and then compare your results with what I have at the end. All right, folks, that's a lot of work to get to our final particular solution, and if that's all you wrote, you would be wrong, because I neglected to consider the domain of the original differential equation. This has a domain restriction. X cannot equal 0, so we cannot have a solution that crosses that asymptote. In fact, for my general solution, I should actually state for x not equal to 0. I don't have to restrict it to one side or the other for my general solution because it's a family of curves. Now for my particular solution, I have to pick a single open interval where the graph of this solution curve is continuous. Because my x value was negative 3, I'm going to say for x less than 0. And now that solution is correct. Folks, my notes are also posted online, so you can take a look there if there are any particulars here that you didn't pick up by watching the video.